Ready to go. Have a good session.
Thank you. So welcome everybody to the low complexity crypto session. We have 3 talks about very interesting papers. I'm really excited to hear them. Lisa, are you here for the first talk?
Yes, I'm here. I'm ready.
Hi. Okay, so the first talk, do you want to share?
Yes.
So the first talk is about low complexity weak PRFs in AC0 mod 2 by Alette Boyer, Geoffrey Couteau, Niv Gilboa, Yuval Ishai, Lisa Cole, and Peter Scholl, and Lisa will give the talk.
Thank you very much for the introduction, Moore. Yes, so hi everyone. I'm very happy to present this work here today. What we considered in this work are weak pseudorandom functions, which are keyed functions that are indistinguishable from truly random function, and where the weak just means that we only require this to hold for uniform inputs. And the security notion we consider is sub-exponential security, which is also what you would expect for a standard assumption like learning with errors and factoring and others. And yeah, in some sense, just the landscape looks completely different if you consider other security notions. And weak pseudorandom functions, even though it's restricted to the input you consider, have many, many applications. For example, you can use them for symmetric key encryption or for identification between parties holding the same keys. And so why do we consider weak pseudorandom functions in low complexity classes? So there's many reasons to do so. First of all, they often directly imply very efficient low-end cryptographic primitives. There's very strong connections to learning theory. So automatically, if a weak PRF is in a class of function and this then this class cannot be learned under the uniform distribution. And we have many examples where weak pseudorandom functions or pseudorandom generators in low complexity classes have direct implications to indistinguishable obfuscations, MPC with certain properties, and so on. And the low complexity class we consider in this work is AC0 invariants. So the AC0 is the class of circuits with constant depth and polynomial fan-in. And we consider AC0 on top of parities, where the bottom layer is allowed to be a layer of XORs. More generally, we consider AC0 mod 2, where the XOR layers are allowed to be arbitrary layers. And we consider, on the next slide, you will also see ACC0, where there's arbitrary mod gates, mod 2, mod 3, and so on at arbitrary layers. And so how does the landscape look there? So by the famous result of Lineal Mansour Nissan, we know that there can be no weak pseudorandom functions with better than quasi-polynomial security in AC0. So this is too low to look at. And on the other hand, in ACC0, we already know since 2018, we have candidate weak PRFs even just with mod 2 and mod 3 gates. So we focus in this work in the area in between. And from recent work, we know, or we have a candidate weak PRF computed by an X and F formula, which is DNF, where instead of disjunctions, you have XORs. And so what we do in this work is go even a bit lower and get a candidate weak PRF computed by sparse F2 polynomials. And further in AC0 on top of parities, previous work, previous construction of weak pseudorandom function was later shown to be broken in quasi-polynomial time by a so-called algebraic attack. And what we do also in this work is, in some sense, fix the attack and fix the candidate and bring forward a new candidate that's currently the only one we know of that we can conjecture to have sub-exponential security. And to give a very, very brief overview of how our candidates look like, how our work looks like. So if you look at the candidate weak PRF in AC0 mod 2, the previous one, which can also be viewed as learning parity with variable density noise, but you don't have to parse the equation here. The only thing you have to notice is that this is basically a sparse multivariate F2 polynomial inputs and their negation. And the idea of this work is to get rid of the negation part by, instead of, so in this in this candidate, the key decides whether a variable is negated or not. And in our new work, the key decides instead which variable to choose instead of negated or not. So this is very, very straightforward. It turns out choosing between two variables is not enough. That's the first thing you might try. And the hard part is actually to prove that this resists like so-called linear attacks, which is a large class of attacks. So we can provably rule them out. We can also rule out more attacks. Yeah, but please see the paper for more details. And yeah, the second candidate is the candidate weak pair of an AC0 on top of parities, which can be viewed as learning parity with simple noise, where the noise is an AC0 circuit, but not applied to the input, but applied to the input times the key, which defines the parity layer. And the problem is that this can be broken quasi-polynomial time, basically because G as a rational function has low degree. And what we show in this work is that you can do the most straightforward thing, very simple thing. You can add another layer, and you actually, this is not, oh, we don't know how to break it, but we can provably show that this has high rational degree other than the previous candidate, and also give very high, or give based on a conjecture, we can also show that it resists linear attacks. It's simple combinatorial conjecture. And yeah, there's much more as you can see here that I would like to tell you about, but I'm out of time, I think. So please check out the long talk and the papers. We also consider the question of weak pseudorandom functions in AC0 on top of public parities and connections to the linear IPPP conjecture, and we give implications of the existence of weak PRFs or connections in AC0 mod 2 and other conjectures. So thank you so much for your attention.
Thanks, Lisa. So I think we'll keep questions to the end of the session for all talks, and we'll move on to the next talk. Mahimna, do you want to share?
Yeah, just give me a second. Can you see?
Yes. So the next talk is about MPC friendly symmetric cryptography from alternating moduli, candidates, protocols, and applications by Itai Noor, Stephen Goldfeder, Tzipora Halevi, Yuval Ishai, Mahimna Kelker, Vivek Sharma, and Greg Zaverucha. I hope I didn't mispronounce anyone's name. And Mahimna is going to give the talk.
Thank you for the introduction. I'm Mahimna. I'm a PhD student at Cornell, and I'll be talking about our paper on MPC friendly symmetric cryptography. And this is joint work with people all over the world. So let me start with some motivation. So symmetric primitives have been used like everywhere, but recently for many applications, there's been a demand for evaluation in a distributed setting, where the keys and inputs are secret shared among many parties. But standard constructions like AES and SHA were optimized for centralized evaluation and not really with this distributed setting in mind. So this kind of creates a natural research direction to design so-called MPC-friendly primitives. And our work kind of explores continues the exploration of this area. So we designed MPC-friendly primitives with the following goals in mind. First, we want the constructions to have as little nonlinearity as possible, since typically nonlinear functions are the evaluation bottleneck. So we'll have low nonlinear depth and small nonlinear size as the design goals. And second, for security, having a high algebraic degree is beneficial to resist learning attacks. And we'll also focus on simple designs since they're easier to reason about and cryptanalyze, and also less prone to implementation errors. So our work continues this research direction started by Bonnet et al. And continued by John et al. And they proposed this alternating moduli paradigm where the basic idea is to compose linear functions over different moduli. And since most of the computation is linear, it should be easier to evaluate an MPC. And the hope is that these mixing of different moduli is enough to resist attacks. And a lot of careful cryptanalysis was done by the two works that I mentioned. So Bonnet et al. Started with this sort of candidate weak PRF. Their main construction was this 2-3 weak PRF, which mixes linear maps over Z2 and Z3. So for this, there's first a secret linear map over Z2 with the key, and then the output is converted to Z3, which is then mapped using a public linear map over Z3. And one reason why this is conjectured to work is because, as it turns out, linear maps over Z2 have a high degree over Z3 and vice versa. So our work kind of continues the exploration of designing new candidates in this alternating moduli paradigm. So while Bonnet et al. Only considered PRFs, we asked whether we can construct candidates for other primitives like one-way functions and PRGs. So we also present a candidate weak PRF where all of the key input and output are over Z2. And for all of our candidates, we perform substantial cryptanalysis and use that to inform our parameter choices. And later we'll give efficient distributed protocols in several different settings with semi-honest parties. And finally, we talk about some applications for OPRFs and signatures. So our candidate 2-3 one-way function, which is what I'll first introduce, follows the same structure as the 2-3 weak PRF, except now the key is replaced by a public matrix A. So now you have a public linear mapping over Z2 using A, and then a public linear mapping over Z3 that uses B. So it's basically the similar structure as the 2-3 weak PRF. And I won't talk about cryptanalysis in this talk, but I'll mention that we found an interesting attack based on reduction to subset sum, which influenced our parameter choice. I'll also very briefly mention our other candidates. So we provide an LPN style weak PRF where the input and output are over Z2. And for this construction, to get the intermediate vector, we add kx mod 3 mod 2 to kx mod 2. And this can be sort of thought of as a deterministic LPN instance with noise rate 1/3, which is given by this vector V. And now, as before, you use this public mod 2 map to get the output. We also provide a candidate doubling PRG, which has the same structure as the LPN weak PRF, but now, similar to the one-way function, we replace the key with a public matrix. And more detail can be found in our paper. So we performed extensive cryptanalysis and used it to influence our parameters, and we primarily considered combinatorial and statistical tests. We found, based on our analysis, that the one-way function and PRG candidates can have S-bit inputs, which is minimal for S-bit security, but we definitely welcome more cryptanalysis. So we focus on the semi-honest setting for our protocols and provide protocols for many distributed settings with and without preprocessing. And our main efficiency gains are from these use of modulus conversion gates that can convert between shares in Z2 and Z3. And we provide efficient protocols for these gates, as well as techniques to generate the correlations efficiently from OT correlations. And our preprocessing is PCG friendly in that the correlations for multiple instances can be generated with sublinear communication. And the cost to generate these correlations is about 1.38 bits for Z2 to Z3 and 6 bits for Z3 to Z2. So based on these, the protocol that we propose for the weak PRF candidate of Bonnet et al. Is about 2x better on all fronts, and primarily due to our use of these modulus conversion gates. So in terms of applications, we provide two OPRF protocols that are much faster than DDH-based OPRFs, but have a slightly higher communication cost. So in fact, our OPRF protocols are even faster to compute than a single elliptic curve point multiplication. We also use our one-way function candidate for picnic-style signatures that use MPC in the head, and we get smaller signature sizes when compared to using picnic over low MC. I'll also highlight that our candidates should be competitive for a number of distributed settings like symmetric searchable encryption, hierarchical key derivation, or generating function secret sharing keys, and details for these can be found in the paper. So just some final remarks. I'll say that the space of simple designs for symmetric primitives is still very much unexplored, and more cryptanalysis is definitely needed. And as for some open directions, it would be nice to have constructions for other primitives like block ciphers or hash functions. And also efficient protocols with malicious security seems like a natural follow-up question. And I'll conclude here. Here's a link to the paper in case you want to check it out. Thank you.
Thank you, Mahimna. Jaya, are you here for the next talk?
Yes,
Yeah.
I'm ready.
Okay. So the next talk is No Time to Hash on Super Efficient Entropy Accumulation by Evgeny Dodis, Siaugu, Noach Stefans Davidovich, and Jaya She. And Jaya will give the talk.
Thanks for the introduction. My name is Zhiye Xie. This talk is based on a joint work I did with Evgeny Dodis, Siyao Guo, Noah Stephens Davidovich. How does Windows time generate random bits? First, it will convert low entropy sources from the environment to high entropy states and send them to a hash function to generate random bits. We focus on the entropy accumulation procedure. It can be modeled as follows. A register R of 32-bit long is used to accumulate entropy. The entropy source x1, such as an interrupted timing, is also a 32-bit string. To update the register R, one needs to cyclically rotate the bits of R by a fixed rotation number, phi, and then XOR the result to xi. This updating process is repeated, and the 32 entropy sources will be accumulated into R. In practice, Windows 10 has implemented this entropy accumulation procedure in its 32-bit CPU. For 64-bit CPU, the implementation is similar. As our main focus, Microsoft's design raises a lot of questions that we would like to answer. The first question is that, can rotation indeed accumulate entropy? We really want to know whether the register R can convert to a high entropy state after receiving 32 samples. If rotation works, then we want to know how Microsoft selected this mysterious rotation number, phi. Finally, is rotation really the best way for entropy accumulation? To start answering these questions, the first priority is to model interrupted timings, which are primary entropy sources in Windows 10. First, we will assume samples are independent, which is the simplest non-trivial setting. Second, the mean entropy of each independent sample is lower bounded by some parameter k. Finally, we will further require each sample to come from some family of natural distributions because we want to model interrupted timings by discrete Gaussian, exponential, or uniform distributions. We have modeled this type of distribution and call it two monotone, where the probability mass function has at most one peak. Any two monotone distribution has most of its entropy in its lower order bits. With entropy sources being modeled properly, now we are prepared to present our result. First of all, by the property of two monotone distribution, we can show that any rotation on n bits with rotation number alpha co-prime to n can accumulate nearly n bits of entropy within n steps. If alpha is not co-prime to n, then the register R will end up with little entropy for some distributions. The first result justifies the use of rotation, but only if we are willing to wait n steps. It fails to distinguish between rotation by 1 and rotation by phi, where the former is obviously the worst rotation in practice. To do this, we introduce a simple quantity, which we call covering number. Intuitively, it's the process of covering a black segment of length n using a short red segment of length k. Every time the red segment is cyclically rotated by a constant alpha. Covering number alpha k counts how many times are needed for the red segment to cover the entire black segment. In our work, we show that covering number is the right measurement of samples to accumulate nearly full entropy from any natural distribution with entropy at least k. This suggests comparing rotations according to their covering numbers. If rotation has relatively small covering numbers for all possible k, then it's a good one. In our work, we show that Microsoft's choice of phi is reasonable by comparing its covering numbers with the optimal value n over k and other rotations. Above two results can immediately generalize to cyclic permutations. We have also constructed a permutation that we call beta reverse rotation, Tor n. This cyclic permutation has a nice property. For any k, the covering number is nearly optimal. So beta reverse rotation has small covering numbers for all k simultaneously. By comparing the covering number of Tor 32 with that of rotation by phi, our study suggests that beta reverse rotation seems to perform at least as well as rotation and better in several regions. Let me quickly recap what I have seen so far. We justified the use of rotation in Windows times random number generator as long as rotation number alpha is co-prime to 32. We also justified Microsoft's choice of rotation number phi by covering number. Finally, we suggested replacing rotation by bit reverse rotation. This one closes my talk. Thanks for listening.
Thank you, Jie, and thanks again to all the speakers of this session. So maybe you would like to open your cameras so that people can ask you questions. So you can either just unmute yourself and ask, or write in chat, or on Zulip. Okay, so let me start us off. So Zia, I have a question for you about the two monotone distributions. So it's kind of,
yes.
It's kind of orthogonal, but I was wondering what you can do with this for standard extractors. So I'm thinking if I don't want to wait n time steps or 5 time steps, I don't have multiple samples. I just have one sample. But if I restrict my distribution to not just having high min entropy, but also being too monotone, so can we do something which is simpler than standard extractors? Did you think of this? Do you happen to know?
It's a good question. Yeah, maybe I need to think more about it.
Okay. So, but do you think that the intuition for these distributions are that they have the entropy and the low order bits? So if I just take those low order bits, would that, is that something like that makes sense at all, or is it totally off? Because for example, if it's just the example you give is the one that's uniform on the least significant bits, that would be great to extract that way, but I'm not sure for the Gaussian or others.
Yes. So for the two monotone distributions, you are right. The most prominent feature is that lower order bits have high entropy. So I guess your point is to just extract those lower order parts, and you want to concatenate them together to form a high entropy one. Is that your point?
Yeah, something like that. I mean, that would be the natural thing to do, right? Start with the low order bits.
So I think it's a good question, but in our context, our entropy accumulation process, the key point of our entropy accumulation process does not know the exact number of mean entropies of the source. So we want this
right.
procedure
You don't know what K
yeah.
is. Right.
So we want it to work to be good for all possible K. So we develop the theory of covering number, and we hope it can solve this dilemma.
Okay, thanks.
Thank you.
I mean, maybe I can add very quickly, you know, Zhi gave the right answer, but our entropy accumulation result is surprisingly good. So basically, for the first couple of steps, we really accumulate K steps, and nothing, I mean, I don't know, not much, you know, can be faster than cyclic rotation and XOR. So in this sense, despite not knowing K, we really accumulate entropy very fast, but you're right that at the very end, if you really want to extract as opposed to accumulate, things start to get really slow at the last few things. So for this thing, probably something, if you really want to extract kind of towards the end, you should probably do something else. But for our application, this is kind of not relevant because anyway, extraction happens somewhere else in the RNG. But it's a good suggestion.
Okay. Thanks, Jay, and also Evgeny. Any other questions?
So I asked my question on Zulip, but this is for the MPC Friendly Symmetric Cryptography paper. Is the OPRF you construct post-quantum secure?
So it should have possible post-quantum security. It's possibly possible.
Okay, thank you.
So also, Mahimna, maybe you can say something about why it works that I mean, your construction, you output multiple bits. The original one, the Bonnet one, only outputs 1 bit, right? So can you say something about why this still works?
So I'm not an expert on the cryptanalysis, so I might want to defer that question. But at least for the LPN weak PRF, there's this understanding that the final Z3 mapping, final Z2 mapping using the public matrix kind of gets rid of our initial expanding of the intermediate vector for the LPN weak PRF at least.
Okay.
So another question I also wrote on Zulip for Mahidma. So did you look into the clear text performance of your weak PRF constructions compared with, say, standard block cipher constructions or something?
So we didn't compare to like standard like AES or anything, but we did have a centralized implementation, just a clear text implementation of the weak PRF. And I think for a reasonable AWS instance, I was just pulling the numbers actually. It's, I think, 165,000 per second, computations per second.
Okay, thanks.
So there's also a question for Lisa, asking which attack techniques against your constructions seem to be the best.
Okay, thanks for the question. So for the first candidate, it seems that LPN-like attacks, so everything, Gaussian elimination, BKW, these kind of attacks that can all be cast as part of the linear attack framework are the most relevant attacks. And it's even shown. I mean, this is below what we actually achieve with our candidate, but there's a provably, but that it can't be more secure than square root of n in the input lengths for X and F formulas. And the algebraic attack, it's also very straightforward to show. So we show it has high rational degree, but that seems not the most relevant there. And for the second candidate, like before we started with the candidate, like certainly the algebraic attacks, because this was the attack that broke the previous candidate, so that was like the one to overcome. And now, yeah, we rule like it could still be that it's close to, it has close to high rational degree. So it's but I would be very surprised about that. So it's hard to say which kind of attacks now are most promising. And yeah, also for the linear attacks there, you can say, well, we didn't rule them out. We just ruled them out on a conjecture. But it's yeah, it's also it's hard to say for me. I would be surprised if it's broken by either linear attack or algebraic attack in this point. So maybe something completely new, or hopefully it's just yeah, secure. We can have further evidence in the candidate. Thank you.
So Lisa, I also wanted to ask you about so your first construction, the weak PRF and AC0 mod 2. Can you say something about the degree? Like how low can the degree be?
So like how large from the input size, or?
I mean, the construction where you choose, where you, instead of negating the inputs, the key now chooses an input, right? So there are terms there, like DNF terms, right? And I wonder, so, and that determines the degree?
Yeah, so these have quite high degree. So you have to, so first of all, like we have to choose between the DNF go up to something in the order of the security parameter. So that will be the degree of the function.
And is that because you want quasi
Sub-exponential security, yes, yes.
And if you wanted only polynomial, do you happen to know what the degree could be?
Yes, then you can I just a second go back to the slide again? So basically the D here that you see, that's also for the previous candidate.
You're not sharing. Did you mean to share?
Yes, just a second. What you see here, D, this D determines like how high the J gate goes. So basically, to get 2 to the security against 2 to the D samples, you need I'll go up to D. So if you so if you have quasi polynomial, then this can be something like quasi polynomial degree. Yes, thank you.
Okay. Any last questions? So I think we'll end here. I'd like to thank all the speakers again, really great talks. And we're starting